Hello everyone and welcome back to our Python Climate Health Data Science workshop. I'm Chi. If you have followed our videos until now, congratulations, because we have already made quite some progress. And now we are already in the day 3 section of our tutorial series. To give you an overview, from here, we will start to learn how to work with real environmental and climate data. And to start with, in today's session, we're going to explore Rasterio, which is a fundamental and powerful Python library for working with geospatial raster data. And before we dive into the code, let's again refresh our brain about what raster data actually is and why it is important. Looking at this diagram here again, we can see the fundamental differences between vector and raster data. So vector data represents features such as points, lines, or polygons, and these can be, for example, a well location, a road, or a pond in real life. And raster data, on the other hand, divides the entire area into a grid of cells, and each cell in this grid will hold a numerical value, which, for example, could be a temperature measurement or even a simple 0 or 1 to classify land versus water. And in today's tutorial, we're going to learn how to use Rasterio. And Rasterio is an open source library that helps us read, manipulate, and write raster data. So first, let's look at how can we load a raster data set. And for our practical example, we will be working with the climate data from the Climate Hazard Center at UC Santa Barbara. Specifically, we'll be working with the maximum daily heat index values. And just to give you a little background, heat index is a common metric that widely used in climate health study. It combines air temperature and humidity measurements to give us a more accurate picture of how the weather actually feels to people. So it is a combined measure of air temperature and humidity to measure humans' comfortability in terms of heat. And the temperature data used to calculate the heat index actually comes from chirp study, which use both the weather station measurement as well as satellite data to create a comprehensive 5-kilometer grid of daily maximum temperatures. And this is crucial because, as we'll see, many areas of the world don't have direct weather station coverage. And in fact, around 4 billion people live more than 25 kilometers from a weather station. Now, let's set our working environment. So first, we will need to import several key Python packages. The most important ones are Rasterio, which will be used to handle our raster dataset, along with some supporting libraries, for example, NumPy for numerical operations and GeoPandas for geospatial analysis. Also, we're importing a new package called Raster Stats, which we will use the Zonal Statistic module. And this is another very important library when we're working with raster data. And for the purpose of this workshop series, we will select only a 1-day heat index image on the first day of July in 2016 and clip it to the extent of Ghana for our analysis. So first, let's have an overview about the daily maximum TIFF files that we have. And these files are stored under the data folder under the heat index heatmax 2016 directory. And you can see that they're all sorted according to the date. So here, if we run this code, which will search all the TIFF files under this folder and sort them according to the date. And if we print the first 5 files, we can see that it starts from January 1st until January 5th. And since we'll only be analyzing the heat index on July 1st, and in our file structure, it is the 181st TIFF file. And to access this TIFF image, we'll use the Python index method, and here we use 182. This is because it's exclusive. And now let's load our file using Rasterio. And the process is quite straightforward. We'll just use the Rasterio's open function to read our file into a Python variable. In this case, we call it himax. And When we examine what type of object we have created, we'll see that it is a Rasterio IO.dataset reader type. And this is different from what you might be familiar with if you worked with GeoPandas before. And the dataset reader has its own unique structure and methods for accessing and understanding data, and we will learn this more later. And one of the most important attributes of our raster datasets is the meta attribute. And let me explain why this is crucial. So the meta attribute contains several essential information about our raster datasets that are stored as a Python dictionary. And this means that we can easily access different pieces of information using the keys. And we'll also update these values later if we need it. But first, I want to ask you a question. So what kind of information do you think the meta attribute actually provides? You can take a moment to think about, and if we print this function, we can actually see what kind of metadata we can access from this function. So from the result, we can see several important pieces of information about our raster data. The driver tells us that this is a geotiff file, which is a common format for geographical raster data. And also our data values data type is float32, meaning that they are decimal numbers with 32-bit precisions. Again, we also have the no data value. In this case, we know that is minus 9999. And also we have the dimension of our raster data. We know that it has the size are 91 pixels wide by 130 pixels high. So each of these metadata elements is crucial for understanding how to properly work with and interpret our raster datasets. And we can access any of these values using the standard dictionary syntax in Python as shown in this case. So if you want to access each one of the the metadata elements, you can specify, for example, the D type or the width or also the height. As we explore this data further, we need to remember that understanding the metadata is very crucial for working with raster files effectively, because it tells us everything from the spatial extent to the data type and also the coordinate system that we're dealing with. So now let's actually read and work with the data inside our raster file. So geotiff files, which are common in geospatial work, can contain actually multiple bands or layers of data, and you can think of how a satellite image might have separate bands for red, green, and blue colors. In our cases, we have a simple structure with just one band containing our heat index value. So here, to read this data, we'll use the read function from Rasterio, and when we call himx.read1, the one is referred to the first, and in our case, the only band. And what we get back is a 2D dimensional NumPy array, which essentially gives us a grid of values. And looking at our output, we can actually see that our temperature is around 39 to 40 degrees Celsius, which represent heat index measurements. And you will notice that in the bottom of the array, there is a bunch of minus 999 values, and these are our no data values that we saw earlier in the metadata, which are represent areas where we don't have a valid measurement. And now we can also check the data type and also the shape of our data set. And if we look at the shape, we'll see that is 130 by 91, and this matches with what we saw before in our metadata earlier. And the data type here is NumPy array, specifically containing float32 values. And again, the structure of rows and columns is crucial because it allows us to work with our data as a grid, where each grid represents a specific geographical location with its corresponding heat index value. And now that we have our data loaded, let's visualize it. So we can use the matplotlib.imageShow function to display data as an image, and with the color bar function to activate our legend. And if we run this code, what we're going to see is that if you look closer at the result map, you will notice something doesn't look quite right. because the ocean appears to have very dark purple color while our temperature data on land is all compressed into the yellow region. And if you look at the color bar, the legend here, you can see that the starting value is a number that are extremely low. And so you will realize that the issue here actually stems from our no data values. Because remember those minus 9999 value we saw earlier, they are causing our visualization problems. Because even though we specify this value in our metadata, but the plot.image_show function is working directly with the NumPy array and doesn't know about our metadata specifications. So here are two ways to actually fix this. The first approach is to manually set the visualization range using the vim function. We can set the vim equal to 0, which will effectively tell MATLAB to focus on our actual temperature values. And if we plot this, we can actually see that this gives us a much better visualization where we can see some temperature variations across Ghana. And however, there's an even more robust way to handle this. We could just directly create a mask to filter out these no data values entirely. So here, first we can read the heat max as a NumPy array, and then we can, using the NumPy's masked where function, we can tell Python to specifically ignore all those minus 9999 values when plotting. And then we use the image function again to plot the mask data. And now you can see that this gives a more clean visualization, and we can see the temperature patterns across the country with values ranging from some 30 to almost 40 Celsius degree. And you'll notice that in the second plot, the color scale is much more meaningful, and also you can see more gradients in the plot. So this method is actually generally more preferred when working with raster data that contains no data values because it gives us the most accurate and interpretive visualization. Now, we can also look at the distribution of our heat index values. First, again, we take our original array, which has a shape of 430 rows and 91 columns. And to analyze the distribution, we need to flatten this 2D array into a 1D array using the numpy.flatten function. And as you can see, now the array underscore f has almost 11,000 individual values, and that's every single cell in our raster. But however, we still need to clean our data by removing those no data values that we dealt with earlier. And after filter this out, we can see that now we have around 10,000 cells in our raster dataset. And now we can just use the hist function that we learned previously to create a histogram of the distribution of our heat index. And look at the histogram we created, we can see the distribution. The data appears to be roughly normal, but slightly skewed, with most values falling between around 36 to 40 Celsius degree. And the peak of the distribution is around 36 degrees, with fewer areas expressing the extreme temperature as either end of the range. So moving forward, let's now explore how we can perform mathematical operations on our raster data. And because raster data is stored as NumPy arrays in Python, we can easily perform calculations on them. And one important thing to remember is that when working with multiple raster, they must be properly aligned, meaning that they need to have the same size and projection resolution and spatial extent. And now I will demonstrate this with a practical example. So we can convert our temperature data from Celsius to Fahrenheit. And again, first, we'll read our Celsius data and handle those no data values. We'll mask them out. We'll mask out the minus 999 and replace them with the NumPy's num value, which is more appropriate for mathematical operations. And then we'll use a standard formula to convert the temperature from Celsius to Fahrenheit. And notice how NumPy allows us to perform this calculation on the entire array at once, which will efficiently converting all our temperature values simultaneously. And if we run this code and looking at our output array, we can see that the converted value are now in Fahrenheit, roughly ranging from 102 to 104 degrees. And also the NaN values have been preserved where we had no error values before. And also we can plot these data in Fahrenheit, and now you can see that also on the legend, temperature unit changed. And if you want to save this new data, and to do this properly, first we could can specify the output file path, and in this case, we're storing it under the data folder, and then we add a meaningful name here. We add a Fahrenheit at the end of the file name. Then we first make a copy of our original metadata, and this will ensure that we maintain all the important spatial information. And finally, we can use the Rasterio's write function to save our converted data to a new geotiff file. And the new file will have all the same geographic properties as our original, just with the values now in Fahrenheit instead of Celsius. So if we run this code, and if we click the data folder, we can see that we have just created, because you can see the modified time is 8 seconds ago, we just exported this Fahrenheit heat index as a geotiff file in our data folder. Okay, now we're going to apply what we have learned so far to a real-world example. That is analyzing the heat index patterns across Ghana's different administrative regions and districts. And you realize that this kind of analysis is very useful for understanding climate impacts and planning adaptation strategies in real-world case. So the concept we'll be using is called Zonal Statistics, which allow us to summarize raster values within specific geographic areas. And it is a method of summarizing or aggregating the raster values intersecting a vector geometry. For example, you can think of this as calculating things like average, mean, or maximum temperature for each region or district, rather than looking at individual grid cells. So for this analysis, we will need 3 key components. First, we will need our input zone layers, and these are administrative boundaries of Ghana at different levels. So they can be national, regional, and district. Second, we will have our raster layer. In this case, we're using the heat index map that we have been working with. And finally, we'll need to determine what kind of statistics we want to derive from the zonal statistics. And in this case, we're calculating the mean of heat index. So let's start by loading our vector data from GADAM, which is the database of global administrative areas. It is an open source data that provides administrative boundaries for different countries and regions in the world. And for this exercise, we'll load 3 separate files, and each representing a different administrative level. And so for each level, we'll follow a systematic process. So first, we're going to load the data using GeoPandas, and then we're going to verify the data columns to understand what information we have. So here, for example, now I'm loading the national boundary data, and we have the country name and also geometry and also their ID. And we can also check the shape of our data frame and also plot it. And here we can see that this is on the entire national boundary of Ghana. And secondly, we can do this for the regional. And here we can see the data frame for the regional boundary of Ghana. And similarly, we can also check the columns and as well as the shape. Here we can see that it has 16 rows, which means that we have in total 16 regions for Ghana. And if we plot this, we can see that now we have some more defined boundaries for each regions. And finally, we can have the district level. Again, we can also check the columns and also the shape, and we can see that for Ghana in total, we have 260 different districts. And again, we can also make a very quick plot of the national boundary of Ghana at district level. And now, moving on, we can load our raster dataset, and again, we will be using the July 1st heat index to run the zonal statistic. And something to note here is that, so before we have used the plot function and also the image show function to visualize our heat index map, but actually we can also use the built-in function from Rasterio, which is called show function. And one advantage of using the Rasterio show function instead of matplotlibs is that it actually can handle the no data value from the metadata, which will make our visualization more cleaner. And as you can see, this is quite straightforward. So we first import the show module, and then we use the show function to visualize our geotab file, and we can see the map, and it automatically handles the no data values. And also you can even pass a color map parameter to change on the color scheme. Here we're using yellow, orange, and red, which is more intuitive. And also, before we run our zonal statistic, an important technical consideration when working with multiple spatial data is ensuring that they all share the same CRS. And to do that, we need to check the CRS of both our raster and also vector datasets to ensure they align properly. So here we're printing all the CRS information for our dataset, and we can see that from the printed results, they're all in the same coordinate system, which is WGS 84. But if the raster and vector data are not in the same CRS, then we may need to apply a reprojection before we run the zonal statistic. And also, to help us understand how zonal statistics actually work, first we can create a visualization that shows our heat index with the different administrative boundaries overlaid. So in this big chunk of code, we'll create a 3-panel plot to show the hierarchy of administrative divisions, and for each panel, we will plot on the heat index raster using the show function and using the color map of yellow, red, orange. And then we're gonna use the plot function to overlay them with the administrative boundaries. And here we are setting the edge color to be black, and then setting the titles for different vector data. And if we run this code, we can see the different administrative divisions overlaid with our heat index values. And you'll notice that this visualization helps us understand exactly how our zonal statistics will aggregate the heat index value within each administrative boundary from the national level down to each individual district level. So moving on, before we dive into our zonal statistic calculation, let's quickly review Python functions since they are crucial for organizing our analysis. So as we learned before, functions are like reusable building blocks that make our code more organized and efficient. And you can think of them as specialized tools that can be used whenever needed. And here we have a simple example that is a basic greeting function that takes the name parameter and prints hello message. And first, we define this greet function, and we use the def argument, and then you specify the parameters, which in this case will be name, and then it will perform an action. And if we try to greet Ghana, this will print Ghana, and also you can modify the input. For example, here, greet human, then you'll see that it says hello human. And now with this in the back of our mind, we can apply these concepts to our more complex zonal statistic tasks. And we'll create a specialized function, in this case called zonal, that will compute statistics for our heat index. And this function is more sophisticated, as you can see, but follows the same basic principles. So to break this down, you can see that first, our function take three parameters or three arguments. In this case, we have the raster in, which is the file name or path of the raster to run our zonal statistic on. And then we have the second argument, which is the polis in. They are the geodatabase of polygons. In this case, this is our administrative boundaries. And then finally do stats. And this is what kind of statistics matrix we want the function to compute. And you can check a more detailed information for what kind of statistics metric it provides. So to break this down, first, this code will open a raster file, and then we'll grab its coordinate system, and we'll project the polygon boundaries to match the raster coordinate system, and this will ensure that our spatial calculations will be accurate. And then it will run the zonal statistics. And in this case, it will use the zonal stat function to compute our specified statistics. And you can see that here there are some other parameters that you can specify. For example, if you enable the JSON out equals to true, this will format the output in a way that maintains our spatial information. And the all touched equal to true parameter will ensure that we include all the raster cells that intersect with our polygon. And finally, it will process the result and convert the statistic into a geo data frame, and it will preserve the original CRS from our input polygons. And finally, it will return a complete geo data frame that containing both our boundary information as well as the calculated statistics. So now let's put our zonal function to work and analyze heat index pattern at different administrative level. First, we'll start with the national level and then zoom into examining the regional variations. So for the national calculations, we first prepare our data by selecting only the necessary columns from our national boundary file, so the country name as well as the geometry. And then we will specify our raster file path. In this case, we know that it is the 181 file. And then we will choose the mean as our statistical measure and then run our zonal function with these inputs. But first, we need to define the zonal method. And now we can check the results. And you can see that now we have a column called mean that are attached to our GeoPandas data frame. And we can see that these are the mean of the heat index for Ghana at the national level. And of course, we can also print our results. And moving on to the regional level analysis, we'll follow a similar process, but using our regional boundary data instead. So here, the poly-in is modified to regional. And similarly, we run the same approach. And if we print the result data frame, we can see that this is a much more extensive list, but we can see that, the final column here, we have a mean column, which is the mean heat index for each region. And to visualize this regional result, we can also plot a map using plot function and specifying some visualization parameters. And here we can quickly see the average maximum heat index for Ghana at the regional level. And we can see that the north regions are warmer than the south part. And again, we can do this at the district level by replacing the polygons in to the district data frame. And similarly, we can also check the results data frame and plot it. And on this map, we can see the district level of the average maximum heat index across Ghana. It provides a more detailed spatial variation. So, as I briefly mentioned before, the zonal stat function is quite flexible in what kind of statistic matrix it can calculate. By default, it gives us 4 basic statistics: minimum, maximum, the mean, and a count of data points. And this already tells us a lot about our heat index. For example, the extreme, the average, and how many measurements we are working with. But we can also access additional statistics when needed. For example, we can also calculate the standard deviation and range, which will help us understand how much the heat index varies within the region. And the median will give us a more robust average if we have strong outliers, etc. So the choice of statistic really depends on what aspect of the heat patterns we want to analyze, whether it is typical conditions, extremes, or variability. And after we calculate the average heat index of each district, there are many ways to use this type of information to inform climate adaptation and decision making. And to give you a simple example, we can use our analysis to identify districts in Ghana that might need special attention due to extreme heat conditions. And understanding heat patterns at the district level is crucial in a country like Ghana because high temperature can significantly impact public health and daily life. And this kind of analysis can directly support public health planning, urban development decisions, and climate adaptation strategies. So in our example, we will simply define the extreme heat condition using a data-driven approach. And we will specifically look at districts where the mean heat index value are above the 90th percentile. And here is how we will implement this. So first, we will calculate our threshold using NumPy's percentile function. So here we are using the 90 percentile as our cutoff point. Then any district with a mean heat index above the value will be classified as having extreme heat, while others will be labeled as normal. So now we will create a new column called heat stress to store this binary classification. And this will help us prioritize resources and attention where they are most needed. And for our visualization, we'll create a map that clearly shows these classifications, and you can have more control by specifying the different parameters. If we run this code, we can see that the result visualization makes it very clear which districts are experiencing higher heat indices and might need additional attention for heat-related health decision and strategies. So this is a possible example or map that we can make from this type of data. Now that we have finished our analysis, you can export on the GeoPandas as a shapefile. To do that, we can use the GeoPandas to file function and by specifying the file path. And also, if you only just need a tabular data, you can also output them as a CSV. And here, again, you can specify in the output side path, and you can modify this code to store the data to your desired locations.